product to sum and sum to product identities. The names of these identities give away their purpose. The first group, the product to sum identities. Well, these are identities that take products of various trig functions and turn them into sums or differences. For example, this first one, if you had the sine of one angle times the sine of another angle, this identity gives you a way to turn it into the difference of two cosine ratios. Or here's a cosine of an angle times a sine of a second angle. You can turn it into a sine minus another sine. The second set does the reverse. These are the sum to product identities. So if you have the sum or difference of two trig functions, you can rewrite that as a product of a couple of trig functions. This first one, sine of a first angle plus sine of a second angle, can be rewritten as the product of a sine ratio and a cosine ratio. So where do these identities come from? Well, the answer is they come from our sum and difference identities. So I've listed a couple of those here. We did these a while back. Cosine of a sum is equal to cosine, cosine minus sine, sine. Same thing for the difference, except with a plus here in the middle. Well, take a look at what happens if I add these two identities together. On the left, I'll have cosine alpha plus beta plus cosine alpha minus beta. And then on the right, let's see, these two terms here at the back are like terms, so they would disappear, minus and plus. And the other two terms are also like terms. I have cosine alpha cosine beta plus another cosine alpha cosine beta for a total of two of those. Well, all I need to do now is multiply both sides by 1/2. Of course, on the right side here, the 1/2 will simply wipe out the 2. And if you look carefully, I have just derived this identity. It's written around the other direction, but I have cosine alpha cosine beta on one side, and the other side is this 1/2, and then the cosine of the difference plus the cosine of the sum. Again, it's written around in the other order, but it's the same thing. All of the other product to sum identities can be derived in a similar way using those sum and difference identities. And then once you have these, it's possible to make some substitutions in order to derive the sum to product identities. Let's focus though on how we might use one of these things. Here's a simple example. I've got the product of two trig functions. The directions say rewrite this as a sum, and when we say that we mean sum or difference. Well, that's exactly what these new identities are for. I need the product to sum identities. Let's see, which one would be the right one here? I have sine angle times cosine other angle, so that looks like this one. Well, all I'm going to do is substitute the pieces out on the other side. My alpha is obviously 20 degrees, and my beta is 70 degrees. According to the identity, this is equal to the number 1/2 times, and then in here I have the sum of those two angles, so 20 degrees plus 70 degrees. And then the second one, sine of the difference. It's alpha minus beta, 20 degrees minus 70 degrees. And then we'll clean this up as best we can. Let's see, this is going to be sine 90 degrees, and this one is sine negative 50 degrees. Now, maybe if I had read the directions a little bit better, I would have done something differently. This says use only positive angles. And I've ended up here with a negative angle. I can fix that easily enough, and I'll do that in a second. What I could have done, though, is I could have recognized that, look, since you're subtracting angles in all these situations, right, there's always a situation where you're subtracting two angles, you're probably better off than rewriting this thing so that the bigger angle is at the front. And that way, when you subtract, you'll get a positive angle for sure. So I could have started by saying, hey, let's switch the order here. When you multiply, the order doesn't matter. And then I guess I would have used this identity instead to obtain the same answer. We don't have to start over though. We can easily fix what we've got here. Sine of 90 degrees, by the way, that has a nice answer. 90 degrees is a quadrantal angle. It's up at the top here of the unit circle. The sine ratio is the b coordinate, which is 1. So sine 90 is just 1. Okay, then I get to the one with the negative angle. Well, we have a negative angle identity for sine. It's sine of negative theta equals negative sine theta because sine is an odd function. So sine of negative 50 degrees is equal to negative of the sine of positive 50 degrees. And that's really as much as I can do. I don't have any way to work out sine 50 degrees by hand. I have accomplished the directions. I've taken the original product and written it now as a sum or difference. I could, if I wanted to, distribute that 1/2 to each piece for a final answer of 1/2 minus 1/2 sine 50 degrees. And that would certainly be fine. I would say either of these two answers would be perfectly acceptable. And we're finished. Thanks for watching.